Hi class, this video is for Mancova. The good news is we spent a lot of time on Mancova, and that's going to make everything that we do here a lot easier. Because we're essentially just changing one of the independent variables into a covariate. And the process is very similar, and I'm even going to use the same data. So Mancova stands for multivariate analysis of covariance, and it's both an extension of MANOVA and the multivariate extension of Ancova. And it's useful in the same ways that Ancova was. We would have a covariate that helped explain the overall variability in our study. But it wasn't necessarily a dependent variable. It was just something that was there that you knew could affect a dependent variable, but you couldn't separate it from the study, or that you thought it could explain some of the relationships that were in the study. Mancova is basically asking if there are statistically significant mean differences among the groups that you have in the independent variable after you adjust the means by controlling for that covariate. So let's go over a couple of definitions. So CB is going to stand for covariate. It can be continuous, like age, or it can be a dichotomous variable. The idea is that we're going to adjust the values of the dependent variables on the groups that we have in our study. And because we already accounted for that, if we still see a difference in our groups, then we definitely have something. IB is gonna stand for independent variable. Some of the textbooks will say, and some of the older textbooks will say it just has to be a dichotomous variable. Really what they mean, it needs to be a grouping variable, because you can have more than two groups. The DB definitely needs to be a continuous variable. If it's not continuous, you're probably better off doing either logistic regression or discriminant analysis. DB combination. So we learned this also in MANOVA. We have Wilks lambda, Roy's largest root, Hotelling's trace, and PLI. So we're going to get the same multivariate output. We're going to be looking at all those four statistics. But the most commonly reported is going to be Wilks lambda. So some notes on the covariate. So remember, we have like this 100% variability in our study. And what we're trying to do is we want to see how much the dependent variables are going to explain, but we also suspect that our covariate could explain some of the total variability in our study. So we want to add our dependent variables. We want to add this covariate so that it minimizes how much unexplained variance there is in our study. It's okay to have this unexplained variance. It's even called error, which makes people uncomfortable. But at the end of the day, as long as we can minimize that and we can allocate the most into the dependent variables, and in this case into the covariant, then it's probably good. Let me see, I kind of said that. So, and I talked about this also in MANOVA. So the process would be very similar to what we did in MANOVA, but we're doing it in Mancova. So if we find significant differences, then what we want to do as a post hoc is run univariate Ancovas to see in each group to see the relationship there. And if there's still a significance, then you want to go ahead and run your regular post hoc tests, which are going to be your Tukey and all those Bonferroni, all of those post hoc tests. Kinds of research questions that you can answer with your Mancova. So one thing that I should separate here in my notes, the null hypothesis is very similar to MANOVA, but instead of saying that there's differences between the means, but the mean, and for the null that the means are equal, and then the alternative that there's at least one mean that is different. For Mancova, we would do the same thing, but we would call it adjusted population means. Why are we calling them adjusted? Because we're pretending that after we adjust everything by our covariate, after we explained that variance that the covariate explains, we want to see what the mean is for that. And if there's a significant difference, again, we're probably going to be happy. So keywords when writing your Ancova and your Mancova research questions is controlling for, adjusting for, and another one that I've seen is above and beyond, and then the name of the covariate. So those are keywords to tell your reader that you're going to be doing an Ancova. And it's always easier for everyone, for the researcher, for the people evaluating the research, the reviewer, if the type of analysis is hinted at in your research question. That's why I'm bringing this up here. So I just modified one of my Ancova research question to a Mancova one. So does the drug work? Does the life expectancy and happiness rating significantly differ between the three groups after we control for whatever covariate that we have? The drug versus the established. For research questions, do various school assessment vary by grade level after controlling for gender? So just because I have various, that kind of tells me that it's multivariate. You can also say above and beyond gender. Do the rate of graduations among certain states differ by degree after controlling for tuition cost? Which diseases are better treated, if at all, by either X drug or Y drug after controlling for the length of the disease and the participant age. So this one has actually two covariates, which is probably more realistic. So how to do an Ancova and R. I'm not going to go through a full example, but I am going to show you the basic structure of the code. So pretend we're interested in statistical anxiety. There's an experiment, and you have three groups, 3 introductory statistic courses, and they were randomly assigned to that course. And there's different tutoring levels for each one of those classes. So our variables would be the classes, that would be our IB. We would have our test 1, which is the statistics anxiety pretest. That would be our covariate. And a lot of times I don't want to say pre and post, but at least repeated measures, designs, the very first measurement is usually treated as the covariate. And it's usually because of practice effects or there was some kind of training at the beginning. So people want to remove that. Test 3 would be statistics anxiety post test. So after I'm going to give them this statistics anxiety post test, I'm going to control for the very first one, and I still want to see if there's differences between the 3 types of tutoring. I would check my normal assumptions, no pun intended. So normality, QQ plots, Shapiro-Wilk linearity. You can do check residual plots, or you can just go to correlation. You can check the homogeneity of regression slope. So this assumption is specific to Ancova. The rest of them, we're familiar with them. But this one is specific, like we have to do it for Ancova and for Mancova. And then homogeneity of variance. We could use Levine's, we could use Bartlett's, and for multivariate, we're going to use box M test. So the basic structure for running an Ancova would be the same as for running an ANOVA. Here I would use the keyword linear model. Here I have my dependent variable. I have the little squiggly thing. Then I would put the covariate. I need to have a plus sign, and that plus sign is so important. I wasted like 15 minutes with an error in R the other day because I didn't have it there. And then you would have the independent variable, and you can have more independent variables. I just simplified this example. And then I usually use the summary just to open up everything that got stored into this res variable. Cool. So that's how you would do an Mancova, but we're actually doing a 2x2 Mancova, and we're going to use the same data set that we use for Manova. So researchers have measured participants on their femininity and masculinity. I'm assuming on the ratings in a survey that ask about femininity and masculinity, and other dependent variables. Other measures were self-esteem, attitudes about women's role, and neuroticism. And for Mancova, we're going to use the same independent variables as before. Remember, femininity and masculinity have two levels. That's where the 2x2 comes from. Our dependent variables are going to be self-esteem and attitude. But this time, we're going to treat neuroticism as our covariate. Let me see. Our research question would be, we want to see if the different femininity and masculinity groups will score differently on a combination of dependent variables, basically self-esteem and attitude, above and beyond that neuroticism scale. I'm assuming there's a theory behind this. We're going to use again the master.csv file. Because it's a CSV file, make sure you're using the text-based option and that you check, this is a text-based option, and that you check, what's it called, heading equals yes. Because otherwise it's gonna have two rows at the top and it's gonna look ugly, and then it's gonna give you errors, and that's never fun. So the first thing I did was just to explore my master file. And remember, we had a bunch of, oops. So once the data was imported, I used the summary function, and then inside the parentheses is the data frame master, just to see what the data looked like. And it looks the same as in Manova because it's the same data. I have 9 variables, or 9 columns if you want to think of them. Remember, femininity and masculinity has 2 levels, high and low for each one of them. Really, we're going to focus on esteem, which is column 4, and attitudes towards women's roles, which is 6, and then neurotic is going to be our covariate. And neurotic, the problem with it is that it has missing data. I do need to remove that. I think we did more of an exploration when we were doing Manova. This time I am just going to use brutal force. I'm just going to use the function na.omit from that data frame, and I'm going to store it into nomis. So that leaves me with 307, which is the same that we had last time. Cool. Then I went ahead and checked my outliers just in case, and we didn't find outliers last time. We didn't find outliers this time. Cool. I went ahead and stored everything in no out regardless. It's just easier for me to run the code all at the same time than going ahead and editing things. Because then when I try to run it in R, I'll find a mistake like, oh, you forgot to change the variable name here, etc., etc. So I kind of go through the motions with this. I did not check all of the assumptions because we did check them last time, and I didn't have to create any new data sets for that. However, I do need to check the assumption of homogeneity of regression slopes because that's an assumption that it's exclusive to Mancova. So what it's saying is that there's no interaction between the treatment or whatever grouping variable that you have and the covariate. So if there was an interaction between the groups and the covariate, then we already know that there's differences between those groups, and we probably don't want to do an Mancova. I'm not sure what method you would use, but it would definitely would not be an Mancova or a Mancova. So if the assumption is met, then we can assume the covariate works the same or is the same for all of the groups. And once we remove it, we can see the real differences between them. And when I say remove them, I really mean once we explain it through the analysis. It's very easy to check for regression slopes. And I did a whole piece of code just for it, but you could have checked it just in the Manova. I'll show you when we get there. So the first thing I did was create a new variable called dvs, which is where I'm going to store the two dependent variables for this analysis. So it was esteem and attitudes towards women's roles. Then I ran a linear model, and I store that into output. So a linear model is like ANOVA, Mancova, ANOVA, whatever type of statistical analysis that uses linear data. So it runs all of them, and then later I'm going to ask for the specific one that I want. And it sounds like it's doing a lot because I say it ran all of the analysis, but really all of these analysis that we learn in this class, they're a combination of the same equation, so it's not that hard, at least for a computer. Then remember the structure for the linear model. You always have your dependent variable here. And the reason we have to use cbind here is because if we put two of them there, like it's just gonna get stuck. Like it's not gonna recognize the second one. And here we kind of created it's a column bind, so it's kind of a vector, and it just recognizes it better. It doesn't get stuck, at least. Then you're going to have your covariate, which is neurotic. Yeah. And then I just wanted all of the possible combinations for femininity and masculinity. That's why I put the asterisk there. I could have done femininity plus masculinity plus the interaction between femininity and masculinity, but this is going to do all of them anyway. And then I put the data set. And then here is just telling the same thing, like how to actually create those contracts. Then to actually open up what gets stored into output, I use this function summary AOB. And then I get all this piece of code that has little hashtags over here. But you're just going to see response 1 and response 2, and then you're going to be like, okay, which one is which? Remember, they go into the order that you created them here in the dv variable. So this one is going to be esteem. This one is going to be attitudes towards role. I keep saying that, towards women's role. I'm just going to say attitudes from now on. It's easier for me. So for esteem, we can see the covariate was significant. And we can see the femininity and masculinity were significant. But really, what I want to look at here, let me do another rectangle. What I want is to look at the interaction. And I want that interaction to not be significant. Again, because if it was significant, it means that the covariate is working differently for a certain group. I don't know which one, but it would be working differently for a group. I just put a little star because that's really what I want you to look at here. Same over here for attitudes. Femininity and masculinity were significant. Neuroticism was not. But really what I'm looking at, because I'm checking the assumption of homogeneity of regression slope, is that the interaction between femininity and masculinity are not significant, and they're not. So I'm really liking this. The moment I said it, I got stuck. So it was not significant for either one of those. And that makes me happy. That means that we met the assumption of homogeneity of regression slopes for femininity and masculinity because they were not statistically significant. So here I was a little bit lazy and I just said p-value less than 0.05. Depending on how detailed you want to be, and from what I've read of the APA manual, they recommend that you actually give the actual p-value. It's just easier for replication purposes. If someone wants to replicate your study, it's always better you give the actual p-value. But that's the Professor Estrada's lazy way of doing it. Okay, so let's go into power analysis. Power analysis is going to be tricky for Mancova. And it might be tricky because of the software that we're using. We were using G-Power, and it doesn't really have an option to do a Mancova power analysis. So you can do it two ways if you really need it. You could do a power analysis for Mancova, which we'll learn in the previous class, or you could do a power analysis for Manova, which we'll learn in the previous lesson. you are going to see there's a very big difference between doing one and another. And it actually has to do with the effect size, really. So this is the same power analysis that we did for Mancova. For statistical tests, I checked, let me actually just show you the screen. I checked Mancova, special effects, and interactions because I was interested in that. A priori, I use an effect size that I think is small. It's 0.09. My alpha was 0.05. My power was 0.80. That's, force of habit. Number of groups was 4, and that's because we have femininity and masculinity, but each one of them has 2 levels. The number of predictors was 2, femininity and masculinity, and the response variables for the Mancova would be esteem, attitudes, and neuroticisms. So this is how you would do it if you were doing the power analysis as a Mancova. And if you recall, it recommended at 79 people. And we have 307, so we were cool. So for the Mancova, I'm just going to take the shortest path. I'm going to say I only have 2 groups, masculine and femininity. So my degrees of freedom would just be 1 and -2. I could have also said 4 and then used 3 here. But the more that we add to it, the more people is going to want. I just wanted to simplify it here. But look at what's going to happen if you try to do it with an Mancova version. So effect size, alpha, and power stay the same. My numerator degrees of freedom, I set 1. My groups, I set 2. My covariate, just 1. Neuroticism. That's a big sample size. And I've actually run it the other way with 4 and 3 here. And yeah, it doesn't get better. So yeah, so you would be in a conundrum. Well, not really. Like, if I would definitely go for the Mancova one. Especially because if you're already attempting a Mancova, you probably have that relationship between the dependent variables. But yeah, it does get complicated because you do have to make that decision. Cool. So now we're actually going to run our 2x2 Mancova data analysis. So I am going to use this function called Mancova, and I'm going to write out again my linear model here. So I have the DVs and then my covariate neurotic and my 2 dependent variables, femininity and masculinity, and I'm pointing out to that data set, no out. So I went ahead and only asked for Wilks. Your textbook and pretty much everyone tells you that you could just look at Wilks. It really depends on how you want to report it. Remember, as long as they all have the same outcome, you should be okay. So I only asked for Wilks, and now I can see that I have significance for neuroticism, femininity, and masculinity, but not for the interaction. So here I could have checked the homogeneity of regression slopes as well, sparing myself the previous step. So you can do that, and they're not going to give you different results. I only did the other one because I was introducing the concept, but you can do it here in a single step. What was I going to say? So here I have like the main effects for femininity and masculinity, the interactions, whether they were significant or not, and for the neuroticism covariate. I also have the partial eta square, and you're not going to have it here. However, if you change this option to test equals dot pli, I'll take you to my, oops, no, I don't want it. I went ahead and asked for, you can do multivariate equals t, that's one way. Or you could do this option, which is a summary. You put where you store the analysis, and then you select pli, just to look at pli. I ran that, and then it gives me, remember, pli, under certain conditions, it will equal the partial eta square. So when in doubt, I would always just calculate partial eta square if I need it. You can also use that heaplots package. It has an option for partial eta square. But yeah, this is where I got the effect sizes. So let's go back to my notes just to check on those effect sizes. I was gonna check them later and I got confused. Yeah, that looks right. That looks right. That looks right. And I actually had to fix this one because it should be 0.18. I also mark here where you can also check your assumption of homogeneity or regression slopes. So because the main effects and also the covariate was significant, our next step would be to do individual ANCOVAs for each one of the dependent variables. So now I'm just going to do my ANCOVAs. And I'm going to do two because I have two dependent variables, esteem and attitudes. So believe it or not, R doesn't know which one is the covariate. So we just need to make sure that it knows which ones are the factors, and it's going to interpret whatever that we leave as continuous as the covariate. So that's what I'm doing here, just making sure it knows that femininity is a factor variable, meaning that it has two levels, high and low. I wish that, well, I don't know how to mute this, so we're going to have to deal with it. Just fast forward. And I did it again for masculinity. And again, it gave me this really ugly looking output. But after that, we can look at our ANCOVA. So for this, I am going to use the AOB function. And it's just a linear model again. It's doing ANOVA, ANCOVA, or whatever linear model you can do in here. It's really in how we write it out that it knows it's an ANCOVA that you want. So my dependent variable is esteem. Neurotic is the only variable here that is continuous. So that's how we and R knows that that's the covariate. And then femininity and masculinity, we make sure that it knew it was a factor. Here I just also want the interaction between them. And where to find them in this data set. And I stored everything into ANCOVA.esteem. You don't have to make the names this big or this descriptive. I'm only doing it because they are, because I'm teaching. To open up the results in ANCOVA.esteem, I just use the summary function. And you can see that the covariate, femininity, and masculinity were significant. So I went ahead and found the partial eta square for all of those. And I just honestly just did it by hand. Here I just type in from looking at the output. I did it for all of those three. The next step is going to be to find the adjusted means. So remember, the adjusted means are our regular means would be whatever we calculate as mean for the groups. The adjusted ones are the means that we have after we remove the variability explained by the covariate. So in this case, we need to use a function called effect. Then we tell it we want to find the adjusted means and standard error for masculinity. And from where, and it's stored here in ANCOVA.esteem. I do want to see the standard error. I want to calculate it. And that's why I said true. And then I'm telling it that mask has two levels. And I store everything into adjusted mean dot masculinity dot esteem. I am being very descriptive here because there's a lot of output. So let me show you something in R. If I use summary adjusted mean dot mask dot esteem, this is actually the whole output that's stored in there. I just find it it's a lot to look at. So what I did was I used the function names to see how they will store into that variable. And this is everything that's stored in there. So I am interested in fit, and I'm interested in standard error just for reporting purposes. So that's what I do here. I have adjusted mean, a dot masculinity dot esteem, and then I do $ fit. And then it gives me the adjusted means for high and the adjusted means for low. And it does the same thing for standard error, high and then low. I did the same for femininity, same syntax over here. I asked for the adjusted means and for the standard error, and that's what it would look like. I'm not done. I have to do a second ANCOVA. And in this ANCOVA, I am going to use the attitudes variable as my dependent variable. The same syntax over here. I just stored it in a variable called Mancova, and then the keyword for attitude. When I look at the output for this one, only femininity and masculinity are significant. And then I went ahead and calculated the partial eta square for each one of those. And remember, partial eta square is the sum of square effects. So for in this case, for femininity, divided by the sum of square effects plus the sum of squares residuals. And then I just use my round function so it's clean and it just gives me 2 decimals. I just find the output and are overwhelming, so I try to minimize the distractions. I did it again for masculinity and femininity. Remember, the only thing that changed here is that I am doing it for the Mancova, where we had attitude as a dependent variable. And then I'm gonna scroll a little bit down so we can summarize all this information. So femininity shows significant effects for self-esteem. I have here my F and my p-value, the partial eta square that I calculated. I keep saying by hand, but R did it. And then I went ahead and just summarized the descriptives in a table. So for self-esteem, low femininity, the mean was 16.52. And then I have my standard error, and then I do the same for high femininity. And then I do the same thing for attitude. Here, I honestly find tables easier, and it might be because I'm teaching it. But you might think that it's just easier to write it out and just have M equals, comma, SE equals whatever number. So now let's look at the main effects for masculinity. It was significance for attitudes towards the role of women after controlling for neuroticism. And then the adjusted means for self-esteem and attitudes are in this table. So for the covariate, neuroticism was a significant adjuster for self-esteem, but it was not significant for attitudes. And here I just put all the F again, the p-value that is not significant, and the partial eta square. And then I went ahead and did a correlation. So here I added a square to where the correlations are. And then this p, believe it or not, it indicates p-value. So this is the p-value for each of those correlations. I use a new function, which is called rcore, parentheses, as matrix, and then I just put my data set, and then the columns that I wanted to correlate. It's from this library. Could I have used ggpairs? Yeah, I could have. And we probably did do it in the Mancova lecture. So my write-up for this would be neuroticism is possibly correlated with self-esteem, which is 0.4, not a big correlation. And it was significant because that's a very small p-value, indicating that high neurotics also have high self-esteem. I'm not a psychologist, but that sounds reasonable to me based on people that I know. What does it mean when your covariate is significant? It just means that, remember, the whole goal of Mancova or Mancova is that we remove that variability from that covariate. It's being explained by that covariate. So next we look at our adjusted means. And if we still see significance there, then we probably found something in our study. And it really depends on what you're studying. So the next thing we're going to do is plot, and you're not really responsible for knowing everything in this piece of code. I can tell you I'm using the library ggplot, and we're going to talk a little bit more about it in the theory data lecture in the middle of the semester. This whole code is just so there's a blank space behind the graph, and then the follow-up code is just telling it where to get the means and from what variables, and to create the bar chart. So I did one for self-esteem, and then I gave you the other code for the attitudes towards women's role. And then at the end, I have I put it all together. I describe the cleanup that we did, the assumptions that we checked, that I did my Mancova. Then I went ahead and described the Ancova for femininity. If you were really reporting this, you would continue to describe the Ancova for masculinity. Here I kind of give you the option if you want to write the descriptive adjusted means or if you just want to create the tables. And last, I have this example and I love this example because it's so short compared to what I just showed you. I do have some issues with it though. So results from the pre-test, post-test Mancova reveal significant differences. They went ahead and reported Wilks lambda, the F, and then they reported what they call partial eta square, but for some reason they used this letter instead of the actual eta. And then they reported the correlation. So once you're actually writing a whole article, what you present gets minimized. So you can always hope for that. One issue that I do have with this article is that they only have 2 groups, so they should have just done a hotellings here. It really depends on what software they use. If they use SPSS, it still runs through the Mancova slash Mancova option. So that's probably why they don't know. And this is the end of Mancova.